In this video, we're going to talk about the equilibrium constant, but we're going to talk about heterogeneous equilibria. Now, heterogeneous equilibria is about equilibrium. And now equilibrium is when the concentrations are at the same level. They are not changing. You can see that here. The concentration of the reactants are not changing. And you can see over here, this is the Haber process, NH3, H2, N2. And you can see they're coming down, and coming up, and then they're staying the same concentration. So that is your equilibrium point where you've got equilibrium. And it takes time to get to that point. Okay, now, just to remind you, definition, forward and backward reactions are at the same rate in a closed system. So that's your definition of equilibrium. And there are two types. There's homogeneous equilibria, reactants and products in the same state. And you can see they're all gases right here. And you can see there are different states in this experiment. And you can see that that's therefore heterogeneous equilibria. Reactants and products are in a different state. So we've got different states down here, and we've got the same states here. We're, in this video, going to concentrate on heterogeneous equilibria. If you want to talk about homogeneous equilibria, go to a different video or go to the exam style questions videos. This is heterogeneous equilibria. Now, Le Chatelier's principle, just to remind you, position of the equilibrium depends on the change imposed upon it. And I always use this example, if I punch you, you're going to punch me back type thing, and that's what reactions are like. Okay, if you apply a change to it, it's going to do the opposite of that change. So if a high concentration is imposed, it'll try and lower the concentration through whatever it has to do. Higher pressure is imposed, it will lower the pressure. That's going to the side with the least moles, okay, to lower the pressure. Or if you apply a low pressure, it's going to go to the side with the most moles. If a higher temperature is imposed, it will lower the temperature by following the endothermic direction in the opposite way. If it's a lower temperature imposed, it will follow the exothermic. But again, that's in a different video, but please have a look at those, and you should be comfortable before going through this video in all of these different parts. Now, we've got the equilibrium constant. That's your equilibrium constant. Again, talked about in a different video, so we're going to go quickly through this. There you have it, and then that turns into the equation, which is products divided by reactants. Okay, so products divided by reactants then turns into the Kc. And we're going to calculate Kc this time for heterogeneous equilibria. Square brackets are going to mean concentrations, so you're going to have to use ice tables. Okay, and we're going to do it first of all with this one here. Now, if you look at this, it's different states, and we've got a liquid, a gas, and a solid. Now, that normally should be this, because your products are going to be divided by your reactants, as we've got here, and then we're raising it to the power of whatever is the number or the coefficient in the equation, which there are none, so this is a 1, 1, 1. Okay, and then we look at this, and that's normally what it would be, but this is heterogeneous equilibria. Heterogeneous equilibria, we eliminate the pure liquids and we eliminate the solids. That's really, really important. Okay, if you want to know a bit of background about that, the reason is because the probability of them reacting is 1. It's going to react. You're going to get collisions with a solid. You're going to get collisions with a pure liquid. Okay, whereas anything else, if it's aqueous or gas, there is a probability of that being reacted or collided with that's less than 1. Okay, but in simple terms, just get rid of the liquid and solid concentration, and those concentrations are constant and are omitted in Kc and Kp expressions. Okay, let's move on to the next one. So we've omitted it, and we've got 1 divided by the chlorine. So 1 divided by the chlorine, because we've eliminated these two. So we've taken that out. And if we've got nothing on top, we have to put a 1 in, okay? So 1 divided by the concentration of chlorine. Now, remember I said you've got to do this calculation, okay? You've got to do this calculation, okay, after you've done the other videos. So after you've done the Kc videos, homogeneous, because what we're going to use is an ice table. Okay, so we've got what looks like a fairly simple question for A2, but actually is much more complicated than it looks. So first of all, we've got this reaction up here. We know it's heterogeneous because there's different states. And we've got our numbers. Let's put our numbers to the side and highlight them. Okay, so we've highlighted them. We've got our Kc expression. Remember, if you're in the exam and you're asked to do a Kc expression, you must draw this. Okay, That is your answer, that's your 1 marker, but we're asking you to calculate Kc, give the reaction, and give the units. Okay, so we've got this. So an ice table. Ice table is literally with the I, the C, and the E. And hopefully you've done it before. Initial, change, equilibrium. And then what you do, you go across the top and you put your reactants in. Now you think you'd only need the chlorine, but I need to work out what's left of the chlorine. I've got 17.75 grams of chlorine, 17.75 grams. Okay, but I know some of that has reacted with this. Okay, and I know it's produced this much of the PCl3. Okay, or used up this much of the PCl3 and made this. So here, we've got to work out all of these different things so we know how much of this there is. And this will make more sense as I go through the table. So with the table, I'm going to go PCl3, okay, and then I'm going to go to Cl2, and then I'm going to go from the Cl2 to the PCl5. Now, at the start, the initial part is that for the PCl3, okay, you have been given the startage, which is 71.5. Now, if you do 71.5, and you do a moles calculation. So if I was you, I'd stop the video right now and I would calculate the moles of this, calculate the moles of this, and calculate the moles of this. That's done using mass over molecular mass. And quickly do that. Stop the video and do it. Now, if you do it, you'll find that you have 0. And this is 0.52. And that's your number of moles. Remember, these are all moles. Okay, so they're all moles. Initial, change, equilibrium. So you've got 0.52, and then you've done your other calculation, and you know you started with the chlorine. You started with 0.25. Okay, so 0.25. So you've done your calculation there. Now, PCl5 at the start is 0. So if that's the case, you've got your initials. You know what your initials were. You also know that at the end it was found to contain 40.15 grams of PCl3. Now, hopefully you stopped the video and you've calculated that. That's our equilibrium amount. That's the equilibrium amount of this. That's what was left at the end. So the equilibrium amount was 0.292. Okay, so we've got 0.292. Now the change is the difference between these two numbers. Okay, and the difference between these two numbers is 0.228. Okay, all we've done is taken this number away from this one and found out how much of this PCl3 was used up. Okay, now that means because of the 1-to-1 ratio between here and here, 1-to-1 between here and here, okay, that was also the amount that was used up here. If that's the amount that's used up there, okay, we started with this, we used up that much. If we take this away from here, we will end up with what's remaining, and what's remaining is 0.022. Okay, so we've got our numbers in our ice table, and we've got an amount here as well. If we want to be complete, we also know, because it's a 1-to-1-to-1 ratio, that means we must have made 0.228, and therefore the equilibrium amount is 0.228. But we don't need any of this. What's really, really important, okay, is this number here. This is the equilibrium amount, but we had to work everything else out. It's a really much more complicated question than it looks. Now, if you calculate Kc, okay, from that, you know it's in a 10 decimeter. So if I go over here, that's a 10 decimeter volume. So I need to, at this point, say I've got 0.22. And so if I want to know the concentration of Cl2, the concentration of Cl2 is going to be that 0.022, which are moles, divided by the total volume, which is 10, which is, if I work it out, and hopefully you've done it already, 0.0022. And that is in moles per dm cubed. So we calculated a concentration. So we calculated the concentration of the Cl2. Just to finish it off, a lot of working out here. Okay, you should be quite proud of yourself for doing it. Very hard question, and my students get it wrong, first of all, and then they get it right. So it's a really good one to do. Okay, and then you look at this, and all you have to do is put it into the Kc equation. And if you put it into the Kc equation, that means, remember, your Kc equation is 1 divided by that. So Kc is going to be 1 divided by 0.0022. Let's make sure I've got my numbers right. 0.0022, which will equal a beautiful finish of 454. Okay, I think it is 545. Okay, 454.5. Now, I've done it to 4 significant figures. You can do it to 3. Doesn't really matter. If we then look at that, we've only got 1 unit down here. The 1 unit down here is moles per decimeter cubed. So you need to times it by -1 to get it to the top, which means you'll get decimeter 3, okay, moles -1. Okay, so literally just taken the unit that's down here, times it by -1, okay, and there we have the positive one first and the negative one after. And that, everybody, is how you do a very complicated look in heterogeneous equilibria, and I hope you enjoyed it. So our next question in heterogeneous equilibria is about this equation here. We've got a solid and a solid, and remember that liquids and the solids, pure liquids and solids, are taken out of the equation. So we've got a much simpler Kc expression with just H2 and H2O. Remember, H2O is a gas and it's within a container, so therefore we can do a concentration of H2O, which is not normal. So that's how we do it. Now we've got an initial amount of the hydrogen and a final amount of the hydrogen, the equilibrium mixture, which means we can use that to work out how much water we've got. We move this to the side, okay, and we bring our equation back up. We then go to our ice table again. So again, don't just watch a video, do this yourself. Okay, so do it yourself. So we start off with our ice table and the things we're going to include on our ice table. Now remember, an ice table is moles, okay? So it is not moles per decimeter cubed. Now in the ice table, we've been given hydrogen and we need to work out the water. We don't worry about the other two in this one because they don't make any difference. We haven't been given any amounts or anything like that, so we don't worry about that. So let's start off with the H2, and then let's have the H2O as well. Okay, in our ice table. Now from the ice table, we know the initial one was 6.464 times 10 to the minus 3. So 6.4, let's make sure I get the number right, 6.464 times 10 to the minus 3. And we know that the equilibrium, that was 0. Okay, we know at the end it is 1.01 times 10 to the minus 3. So at equilibrium, 1.01 times 10 to the minus 3. So we've got that. The difference between these two numbers is the change. Okay, and the difference is 5.45 times 10 to the minus 3. So we've got our numbers here. Now that means, because it's a one-to-one ratio, because it's a 4 and a 4. So a 4 and a 4. Okay, so 4 and a 4, and that means this is 5.45 times 10 to the minus 3. And difference between 0 and 5.45 times 10 to the minus 3 is 5.45 times 10 to the minus 3. Right, okay, so we've got our ice table beautifully done. Okay, and then we can go from this to doing our concentration. So we need our concentrations. So remember, it is a 5 decimeter container. So we can do it by going our concentration that starts off with of our H2, and that is going to be our equilibrium amount divided by our volume, okay, which is 5 decimeters. Remember, this is always in moles, okay, and divide by that. Okay, and then that will equal, in the magic of science, okay, 2.02 times 10 to the minus 4. Okay, superb. Right, we then go for the H2O. Okay, and the H2O is going to be equal to that number right there. Okay, and divided by 5. And remember, that is decimeters and that is moles. So we're doing moles per decimeter. And so the concentration of the water is going to be 1.09. So 1.09 times 10 to the minus 3. Okay, so we've got two concentrations. Remember their concentrations, so that's moles, decimeter cubed, moles, decimeter cubed. Okay, so we've got two beautiful numbers right there. We need the Kc expression. Perhaps should have gone about that before, but let's do that now. Okay, so let's do that now. So that means our Kc expression is going to be equal to, so we have products over reactants. The product is the water. Okay, and remember, to the power 4. Okay, then our H2 is also to the power 4. Don't forget the 4s. Okay, so don't forget the 4s. Taking the 4s. I did this once in class, and I was doing it in the class, and I forgot the 4s, and they reminded me to do the 4s. So well done them. Okay, and you put that in, and you will get a beautiful number when you put these two numbers in. And that beautiful number will be 850.3. Okay, so we've got 850.3. We've got some units. Notice, same number of units on each side, 4 times moles per decimeter cubed, 4 times moles per decimeter cubed, so they all cancel, which is fabulous. And what do you remember from earlier videos? Remember, you must write no units, okay? Because you have to show the examiner that you understood. If you just put a blank, they don't know that you didn't know there was no units. You have to write no units. A really good point. So these are two of the classic heterogeneous equilibrium examples. Okay, and they're quite difficult ones. Okay, and they might turn up difference between an A and an A star.